All right, so now that we have a good understanding how neural networks operate and of what components they consist, the next important part is to understand how we, tune them. And we will do that in two steps. In the next chapter, our focus is on quantifying empirical loss. This means I want to elaborate on the mechanisms that allow us to tell whether a network that we have with a given set of weights does a good job. And essentially this helps us to judge the adequacy of the neural network for our task. And once we know how to tell that, how to determine whether the network is good or where it is not good, that's the key ingredient in order to improve the network, to train the network to adjust the weights, as we shall see later. But let's look at the loss. So we will revisit our data set. Remember our tiny credit scoring example with a bunch of borrowers that are characterized by two features, the bureau score and the salary, and where we have one label. It's denoted as default, whether a borrower has paid back all the debt or the credit or not, yes or no. And that will serve as our example for now. So one specific example of this data set, one data point, we could denote it as a vector. So this example here is the first record in our data set. If you study the example a little bit, that's actually John. So the 320, that's just the bureau score of John, right? And similarly, the value of 900 represents John's salary. And we have a blue entry here, which is 1. The blue entry is just John's target or John's label. And we know that John turned out to be a defaulting customer. So he did default it, and we encode, let's agree on us encoding the status default equal to yes with a 1. So the 1 here in blue denotes the target label. And then there is yet one more value of 1, this guy here. And that's going to be our bias. To simplify my notation in the reminder, I did add a constant column of 1s to each record, to each data point x. Because of that, I do not need to carry along the bias in my notation later on. So this is one data point. And now let's assume we take that data point and we feed it into our neural network. So this is also a good exercise to remind us how the calculations work. So we have, say, 900, the salary. So that would go in here. That's our input salary to the input layer unit m, or 3, m equal to 3 in my example. Remember that in my notation, m denotes the number of features. And the bureau score, 320. Well, if you are familiar with credit scoring and bureau scores, you will know that 320 is actually quite a poor score, so no wonder John turned out to be a defaulter. But anyways, so that is the bureau score. And now we see it a bit more clearly here. We take this constant value of 1 as our bias, meaning that any type of weight that the neural network will determine going out from x1 to one of the hidden layer units represents a bias or represents an intercept. And finally, of course, we have our target label 1 default. Well, yeah, that goes all the way up to here. It's something we know for sure about John, something we have observed. And our neural network will now take the input values, so 1, 320 and 900. That's the input layer. And then these values will get multiplied here with a weight matrix W. Or we could say that's W1. It's the first matrix of weights connecting the input layer to the hidden layer. Then for each hidden layer unit, we will receive some scores resulting from the calculation of x transpose W. These scores will go through some nonlinear activation function, the yellow part of the picture. So basically, well, maybe to delineate that a little bit. So this is where our weights live. And then here we have the input to the hidden layer, where all the incoming connections get aggregated, and we used to denote that by Z. And then these four Z values, the input to each hidden unit, will be put through some activation function. So here we've got H, our vector of hidden layer outputs. And then these four hidden layer outputs, or these four latent features, will again be multiplied with some weight matrix, the weight matrix connecting the hidden layer to the output layer, W superscript 2. And this gives us some final result, some final output. If we assume that our weight matrices are properly organized, have proper dimension, then specifically here for W2, the dimensionality will be 4 because we have 4 hidden units by 1. So actually that's a vector. If I'm very rigorous here, I should make it a vector. But, well, maybe this does not really help so much. Anyways. And then we have one final score. So let's say that is a value of 0.65. That's our network output. And let us assume that represents, or is to represent, the probability of the input of the values of the feature values of John, of the input, the corresponding forecast of John being a bad credit risk. Well, we do know, because we are still in the stage where we build our neural network, where we train it, where we have training data, we do know that the true label of this customer John was 1. So we have a forecast 0.65, which we interpret as the network estimated default probability. And we have the true value 1. And this allows us to calculate something like a residual, right? We can now quantify the degree to which our network is accurate in estimating the target label, or the label of our customers, of our borrowers, or the extent to which it's not doing a good job at estimating that label. After all, we had a probability of 65%, which is somewhat going into the right direction. But on the other hand, ideally, knowing that this data point had a label of 1, knowing that John, our customer, was actually a defaulter, clearly we would have liked the network to output an even higher default probability. And the degree to which we judge the 65% compared to the true label of 1 being a good or a bad forecast, now that is encompassed in a loss function that we do need to choose so that it matches the particularities of our task, and I'll denote it with these L here. It's a measure that quantifies the quality of our neural network to deliver good predictions, to deliver good, well, PDs, probabilities of being bad, or good probability estimates. Yi is the actual label, and well, I use f here as a function that is to represent the entire neural network. Meaning, if I write it down in this way, I mean by that this W here, big W, consists of what we had before, W1, the weight matrix connecting the input and the hidden layer. And also, well, I denoted this as W2, noting that this is the weights connecting the hidden layer to the output layer. So f of xi colon w represents the entire output of the neural network. We could equally denote that by y hat or yi hat as our forecast. And the loss function aggregates the true label and the forecast and then puts out a scalar value which captures how good the neural network actually is. That's sometimes also called the objective function, or it's called also the cost function. I think the most popular term, clearly in statistics, but also in machine learning, is loss function. So I tend to prefer this term, but you might want to know that other terms are around as well. And well, just to familiarize yourself with the notation, this measure of loss is something that we calculate for each individual data point, for every example in our data set. So note the small x right here, that's one vector, that's one data point, one borrower, one customer, whatever are the subjects of our analysis might be. For this single data point, we know the true label, at least during the training stage, and then we can compare the network output and the true label in order to tell whether the network delivered a good prediction, a good output. That's embodied in this loss measure, L, and if we aggregate that over all the data points in our sample, that's the total loss. So strictly speaking, our loss function is J, or I will use J of W to denote loss functions, and this guy L here, that's basically the specific way in which we capture the agreement of the network output and the true target value for an individual data point. And what you see here as well is that the loss function, or this value J of W, we calculated at the basis of the entire training set. So note this X here. So we have the entire training set. We put all the data points through our neural network. We have our weight matrices. We have our hidden unit, and then the output of the neural network, f of capital X, is actually a vector of the same dimension as the labels. So f of X is is 1 by n. Remember, small n is the number of data points that we have in our training set. So as the slide is trying to sketch, we get one forecast, one output, one prediction for every data point in our training set. Also, we have a label for every data point, and then we can compare the two, putting them through our loss measure, and then calculate the value of the loss function, which gives us a scalar value that represents the adequacy of our neural network. Right, and one very popular loss function that all of you know is the least square loss, where the specific shape is that we calculate the loss as the squared residual of the true target minus our forecast squared, and then we sum that up. And you also see the shape of the loss function illustrated here on the slide for the residual, and how the magnitude of the loss grows if we deviate more and more from the true target value. Well, this function you know very well, and this picture you know very well. What's maybe more interesting though is the loss, how it depends on our weight matrix W. That's more interesting because, well, X is just the training data. That is immutable, that's given. We have observed a certain amount of training data in the past, X, that is given. And putting this training data through our neural network, we can calculate the loss in the way we just discussed, and then we have a value of that loss, and we might be able to interpret that value and judge that our network is doing a good job or a decent job or a poor job maybe. But how can we do better? The only thing we can change here in the whole picture is W, the weights on the connections in our neural network. These are the three parameters. This is what we can adjust to reduce the loss. So what's a more interesting picture is the loss function and how it depends on the three parameters. And as you know very well, drawing in many dimensions is very difficult. I can't go larger than 3. And in this three-dimensional graph, I assume we have only three parameters, W1 and W2. And then if we also add the value of the loss for a corresponding, very tiny neural network, it's not even a network probably. Anyways, if we add the value of our loss to the picture, we obtain this three-dimensional shape. And assuming that we still use a squared error, that we still use as our measure of loss the sum of the squared residuals, which you see here. M, right? Check whether you have noticed it. Otherwise, if you haven't, make sure you pay attention to the equations. I put them for a reason. That's our measure of loss. And you see this shape of the loss surface. Sometimes we use the term loss surface to describe this picture. What's the shape of the loss with respect to the three parameters, the weights of the neural network. Right, and the loss is something we want to minimize, obviously. So essentially we are trying to set our weights, W1 and W2, and more generally all the weights that we have in our neural network, in such a way that we end up somewhere here in this area, right? It's always difficult to read three-dimensional graphs, but well, here the minimum is centered somewhere where both W1 and W2 receive a value of 0. Clearly that does not make sense, so don't over-interpret this graph. What I'm trying to show here is the shape. And this shape, in the case of this very simple example, which is just a linear regression, is very well behaved. And you can imagine that it's very easy to find this sweet spot where the loss is minimized. And finding the sweet spot is equivalent to finding the optimal values of the three parameters, finding the optimal W, which minimizes the loss And since they minimize the loss on the training data, these would be the W's, these would be the parameter values that we want to use when applying our neural network to novel data for screening credit applicants or whatever. And well, generally, in order to find that sweet spot, we make use of your calculus skills. So we would, in general, look for the derivative, or all the partial derivatives, to be precise, of our loss function with respect to our free parameters. And we would equate these to 0, work out the corresponding values, and for very simple cases, such as this one here, we would be able to work out an analytical solution. Our loss function is very well behaved. The partial derivative of the loss with regard to W is just twice the residual times -1, right? So we have yi minus xiw squared. Finding the partial derivatives of that for all the w's, we have twice the residuals yi minus xiw. And then we have the -1. So this is equivalent to, say, stating that xiw minus yi is equal to 0. That is a very simple case, though, because we have ignored multiple layers, etc. Super simple. And you probably, or at least maybe, you know the normal equations which gives us the way to calculate the weights in a multivariate regression model. So if we basically state that the optimal parameters, let's say, let's use a different color here. If we look for the optimal parameters, W star, the ones that minimize the loss, well, we basically find them by minimization. So that's the argmin of W of our cost function, J of W, which you see spelled out here on the upper part of the slide, so I won't do that again. And then you might know that for linear regression, ordinary multivariate linear regression, the optimal solution is x transpose x inverted x transpose y. This is how we find the least square estimate of W or beta. You know that in traditional regression we denote free parameters by betas. This is how we can easily calculate the optimal weights, the optimal parameters in the case of linear regression, multivariate linear regression. Yet this only works for very simple models, like the regression model, which is a pretty simple model. It would not work in general. In general, for neural networks, we might have to work out these partial derivatives, or we might have to solve the system of equations using iterative methods, relying on numerical optimization, gradient-based methods in particular, and we'll see how that works in the next chapter. But for now, you can take with you that we have our loss function, and typically we minimize the loss function over our free parameters, so with regard to W, and this gives us the optimal values of W and at the same time the final set of weights in our neural network. But before detailing that any further, this squared loss function is only one that we might use. It's the most popular one by far whenever you're trying to approach a regression problem. If y, our target, is a real number, then you would probably use a squared error loss function. Or counting a little bit on you remembering what we did in business analytics, maybe you would not minimize just the squared error loss. Maybe you would add a penalty term to penalize large values of W, adding, for example, an L1 penalty or an L2 penalty, rich lasso, rich regression, lasso. You should remember this principle of regularization. We're going to briefly revisit it in the next session, but only briefly. So it might not always be the squared error loss function that you are minimizing, but if you minimize a more complex loss measure and face a regression problem, the empirical risk, the agreement between your model and your training data, that is typically captured by least square loss or by the squared error. And we do also work a lot with problems where our target is discrete or even binary. Coming back to the credit scoring example, we have defaulters and non-defaulters, and we are trying to tell these apart. So for classification problems, we encode our target Y either with a 1 denoting one class or with a 0 denoting the other class. And or to be honest, it's not strictly wrong to then use squared error loss, but normally it is not done. Normally what we use is the binary cross entropy loss function or log loss function, which well, if this equation looks familiar, well done. You should know it. You should know it from logistic regression in particular. This is our log likelihood function, as it is also called, or binary cross entropy function that we use to train classification networks. And remember, in an application where we face a binary classification problem, like determining whether a credit applicant is a good risk or a bad risk, apologies, and where Y is either 0 or 1, that would be a good way to capture the loss. You see the functional shape, which is depicted for our probability, our conditional probability that a specific case, X, belongs to class 1, Y equal to 1. And if we assume that this case actually does belong to class 1, so if Y is equal to 1 and we output a value of 1 using our neural network, it makes sense that our loss is very small. Specifically, it's 0. And it cannot be any better, right? And you see the shape of our loss function here, of the binary cross entropy loss. The farther apart we are from this optimal value of 1 with our network output, if we forecast, for example, an 80% chance of the data point belonging to class 1, here, that's still a pretty good forecast. If we output a 60%, brings us to here. Okay. Well, actually, it would be nicer. Use purple here. Wouldn't it? But if we are getting farther and farther away from the true value of 1, we only give it a 40% chance of belonging to class 1. You see how the loss increases and how it increases exponentially. So this loss function penalizes large residuals very heavily. That is a commonality with the squared error loss function, for example. This way is the binary cross entropy for settings where Y is either 0 or 1. And if we generalize this a little bit, that is the cross entropy loss function. That's the standard loss function for classification. So it's the equivalent to the least square loss function. What the least square loss function represents for regression problems, that is the cross entropy loss function for classification problems. And it's just the same as the previous equation. Let's convince ourselves that it is. I assume we have multiple classes, and I use the symbol capital C to depict the number of classes that we face. And then the first part of this function here, this bit, is not very interesting, right? We basically sum over all the data points to compute our total loss. This is exactly what we did before. That's a nice setting where we can measure the loss on an individual data point, and then the total loss is just the sum over the individual losses calculated for each data point individually. That's a typical setting, and it's a nice setting. Well, if you think about training a network by minimizing something as AUC would be a lot more complicated, because a measure like the area under the ROC curve, we cannot write it down in this way. The area under the ROC curve does not depend on the individual level classification. To calculate the area under the curve, you also need the classifications, the probability estimates for other data points, right? Because it's a ranking measure. That's not the case for the squared error loss, and it's not the case for cross entropy. So the part here, the left part, is just aggregating over all the data points. And the other part is the one where things are interesting. The one I'm highlighting here in purple, that is the interesting part. And if we have capital C classes, and if we assume, that's actually important, if we assume that we encode our classes as a one-hot matrix, then we know that YIC, the true label of case I, will always be 0, but for the single class to which this case belongs. So YIC will normally be 0 for every class to which the data point does not belong, and it will be non-zero exactly once in this summation. From small c equal to 1 to big C, the number of classes, there will only be one single class to which the data point belongs. So most of these terms will cancel out. Only, that's the take home here, only, and this is our neural network again, the output of our neural network of the unit C. Let's say C equals to 2. Assume C equal to 2. So this means if we draw the vector of two labels here, so there would be 0, 1, 0, essentially. Right? And then only for the output unit that corresponds to the true class, we would look at the specific value, and we would take the logarithm of that output, so we would look at this hidden unit, seeing what's going on there for our data point, what was the probability that the network has estimated for this specific class, class 2, and that estimate would determine the value of our loss measure for this data point. That's the idea of this loss function. And since we haven't worked with multi-class problems so far, I would like to elaborate that in a little more detail. So for now, we have this loss function, the cross-entropy loss function. It's something like the equivalent of the least square loss function, but for multi-class classification problem, or for any type of classification problems actually, because the binary cross-entropy is just a specific case of this loss function. So that is the one to use for classification problems. And let's further explore multi-class classification a little bit. To give you some context, you could imagine the case where a financial institution is trying to classify corporate lenders, corporate borrowers, into rating grades or rating facilities. You will know these corporate ratings issued by, for example, S&P or Fitch or Moody's, where they rank order corporates, big organizations, also sovereigns according to their creditworthiness, and where then a value like AAA would represent a company that is extremely creditworthy and where the risk of the company defaulting is estimated to be very, very low. And then the next best category might be AA and then A, and then we might have something like B plus and C, etc. So we have these ordinal grades, rating grades, that embody how creditworthy a corporate borrower actually is. And in credit ratings, we have in practice something like 11 or up to 15 different grades. And if we mimic such a rating approach, we actually face a multi-class problem with 11 or 15 different classes, where each of the rating categories, AAA, AA, B plus, etc., represents one class. And we have capital C classes overall, and all the classes are mutually exclusive. That's actually important for this type of setting. If I talk about classification or a classification problem, I mean that every data point belongs to exactly one class. And I also mean that all the classes that exist are a priori known. As in this example, if you do credit ratings, you set up a rating system where you determine the number of different rating grades into which you distinguish your borrowers, and then all the classes are known and fixed and given. So no change there. We have C classes and that is it. And what you see in the picture is a simple model, for now only a perceptron or a multinomial logistic regression. Basically, same thing, for almost the same thing. We have multiple inputs again, and we have weights that connect the inputs to our single hidden unit. And then we just have multiple output units, as many as we have classes. That was also the case in my previous example. So here as well, I just had put multiple output units without really detailing that. So now you will understand that even better. For classification problems, especially multi-class problems, we usually configure our neural network in such a way that the number of units in the output layer is the same as the number of classes that we have. And then we can interpret every neuron of the output layer as the model probability for this specific class. So y hat 1 is to represent the model estimated probability of a corporate borrower belonging to class 1. That might be AAA. And y hat 2 is to represent the model estimated probability of a corporate borrower X belonging to the second class, AA maybe. Okay, that's how to read that. And now let's detail the calculations that will go on if we put some data through this perceptron. We have our perceptron model with multiple outputs, and you see the cell and you see the two key operations that go on in each of these computational cells: input aggregation and non-linearity. So if you spill out what's really going on each of these output units, what's really going on at y hat 1, y hat 2, all the way down to y hat c, it's fairly easy to write that down. To not torture you with my awful handwriting, I put the equations here. And well, first of all, we have our inputs, x, which get weighted with a weight, w, and the superscript of these w's is to represent that they sit at the first, or in between the input layer and the hidden layer. So it's the first weight matrix, if you wish, or it is the first set of weights. And you might judge this equation here a little bit as an overkill, because I'm summing from j equal to 1 all the way up to d, where d denotes the dimension of the hidden layer. But in this case, actually, and I should write that down, because I'm starting with the most simple case of the perceptron, so d is equal to 1, which means that in fact these summations, they sort of cancel out. We have an input value, j, and that is receiving a weight, wo, w1, w2, wm. That's basically what's really going on there. And then our hidden unit receives these weighted inputs, sums them up, and then we also, well, and then we apply some nonlinear activation function, g, to that, right? And then we also have weights, w1, well, or here I should better start with w1, w2, w3, and wc, weights that live on these connections. And you see how in this picture we really also need a superscript, or we could equally use a second index, to indicate that these are the first set of weights that we have. And that these are the second set of weights that we have. Okay? And then we have the inputs. We weight the inputs. We take the weighted sum, add some nonlinearity. That's the function g. And then we weight that again in order to compute the input of each output layer unit. Y hat 1, y hat 2, all the way down to y hat c. And well, there is little reason to believe that these outputs that we produce in this way would be well behaved, in that they would sum up to 1, which in multi-class classification is what we want. We know that the different classes, the C classes that we operate with, we know that they are mutually exclusive. Corporate borrower can only belong to one rating grade, never to 2 or more. It's mutually exclusive. And since we would like our model to produce class probabilities, the sum of all the class probabilities, the sum over all the classes, needs to add up to 1, which will not be the case in this simple model. And this is where this softmax function will come in handy. And it's another crucial building block of neural networks, specifically of neural networks for classification. These output that we have in so far are sometimes called scores, or in logistic regression we would call these the logits. This is exactly what they are, if we assume that G is the logistic function. And we would put these through another layer, so-called softmax layer, the task of which is to normalize these scores and to make sure that they add up to 1. And the output of this softmax layer, that is it what really gives us probabilities. And the sum over P, so not 0, that's nonsense, sorry. Obviously that would add up to 1. That's the idea. And so we need another piece of architecture in our neural network for classification in order to make sure that our network really gives probability estimates. And should you feel a little bit lost at this point, we were talking about the cross-entropy loss function earlier on, right? Maybe let's briefly go back to that slide so that we make sure everybody is on the same page. That was our cross-entropy loss functions. And you see the log here. And since we log the output of your neural network, or the very idea of this loss function is that the network output fc of xiw here is an estimate of some probability, is a probability estimate. That's the very idea. It is something that lives between 0 and 1. That is inbuilt in this loss function that we use. So we want our networks to predict probabilities. If we use the cross-entropy loss function to measure the quality of our neural network, we assume implicitly, well, not so implicit actually, we assume that our network delivers probabilities. And what we have learned just now is that our network normally does not produce probabilities unless we make it produce probability. And to that end, we need this softmax operation, or we need this softmax function, or this softmax layer. It will give us a probability. And then, well, if we want our network to produce crisp class predictions, that would also be possible by just adding another operation by which we look at the maximum probability of the set of probabilities, which one is largest. And if we say, well, P1 actually is the largest out of these C probabilities, then we could define, or we could state that the discrete class that our network has predicted is equal to the first class, Y1. This would be needed, so this step here, let me see which color is yet free, let me use blue again. This step here is not needed if we are still involved with training or tuning or tweaking the neural network. Then we typically use the probabilities. You have seen that these probability estimates are the ones that go into our cross-entropy loss function and then matter for judging the quality of the neural network. So we do that in training. Typically also for predictions, that is enough. Prediction. In that we are happy with our network producing probability predictions. This side here, that's something we might need for decisioning. If we make decisions based on a model, on a probabilistic model, then typically we want to select one specific action. And this is where we need discrete outputs. Right. But I'm getting a little bit distracted here. The key point to note is that we have the softmax functions as a crucial part in any type of neural network for classification. And the job of these softmax functions is to ensure that the output units deliver probability estimates. And as a matter of fact, if you also follow the header, where I put standardizing the output of a perceptron for multinomial classification, you could think of this softmax operation. You could think of it as the activation function of the output layer. That is a way to think about it. It is somewhat similar to this function g that we were using in the hidden layer, to this yellow part here. It's somewhat similar. For each of the output units, we receive inputs, we aggregate the inputs, and then we put them through some function, some nonlinear function, to determine the output of the unit. And the output of the output layer units is the final forecast. So if you read through some textbooks or blogs, softmax, you will typically see it as the softmax layer. You will typically see it presented as something, as yet a different layer that we add to the architecture of our neural network. That is fine. You could also think of that as an activation function for units of the output layer. It's really the same as the activation function for the hidden units, just it's applied to the output units, and its purpose is to ensure that these units sum up to 1. So here I wrote it down for a proper neural network, not a perceptron anymore, but it's a trivial extension. And here you also see the equation of the softmax functions, which might be familiar to you. It's the same calculation that occurs in multinomial logistic regression. So it's not all too new. The name maybe is new. In the neural network community, we call that the softmax function, or we sometimes use the term softmax regression. And well, the reason, if you ask why softmax, is that it's something like taking the maximum we get from our neural network, these scores or logits, like the raw signal of the output units, and we look for the largest one, but we don't want to ignore all the other outputs of units that are, well, not largest. And in this regard, it's a softmax. So if you look at these numbers there, where I'm assuming that the first output unit has a value of 2, and the second output unit has a value of 1, and the third output unit has a value of 0.0. Clearly that is the maximum, 2 is the maximum, but we don't want to only consider that value in order to judge our network. We want to have a more detailed perspective, and this is why we're taking a soft maximum, where the second output unit and the third output unit, they also receive some weight. After the softmax operation, we get these probabilities, 70%, 20%, and 10%. And if you follow along the equation, you can convince yourself that it's true, it's certainly true, that afterwards we really have probability estimates. After applying the softmax, our scores will add up to 1. And this is how we build probability predicting neural networks, essentially. If you want to play a little bit with this function, convince yourself that output sum up to 1, etc., there is a nice blog available, which I cite here, and also this little demo script. This demo softmax here, this is a little Python script. It's very, very much based on this blog post. I just cleaned up the notation a little bit so that it agrees with the slides, etc. You find that on Moodle if you are interested. It's in the folder lecture codes. Oh, maybe can I have a quick look? Here we have our GitHub repo, and if you go to Adams and navigate to lecture codes, there is a little demo underscore softmax, this little Python script, which you can play with. And should you use Google Colab and have not set up a Python environment on your computer, it will also be possible to easily turn this code into a notebook so that you can then play with that. Also create this plot. As a matter of fact, the vast majority of the whole code, basically all this part that I'm highlighting right here, is only to create this nice little graph, which shows us really this S characteristic S shape that we know from the logistic function, but in multiple dimensions. Here we have two inputs, Z1 and Z2, and we can visually explore the functional shape of the softmax function. All right, now back to our PowerPoint. Here we go, almost done. If we put things together before moving on with training neural networks, we have already learned some quite important lessons, I believe, concerning the architecture of neural networks. Specifically, I've been trying to summarize that here. We can use neural network for various modeling tasks. That's one of their strengths. No matter what type of task you face, it will always be possible to use a neural network. Regression classification, obviously, but also ranking, survival analysis, whatever. There will always be a way to configure a neural network to address this task. But sticking to some more simpler tasks, for regression, we typically use neural networks that have a single output neuron, where we use as loss function the squared error loss. And then in the output layer, we just take the raw output of our neural network. No need for any additional layer to normalize output. For binary classification, we have seen that our loss function is the binary cross entropy, or log loss. And then in the output layer, we would use a sigmoid in order to make sure that our output of the single output neuron is bounded by 0 and 1. So for binary classification, a single output is enough, because this output could represent the probability estimate for one of the two classes, and then obviously the probability estimate for the other class is just 1 minus that. And then we would use in our output layer the sigmoid function to ensure that the output of our neural network really is bounded by 0 and 1. So the raw score, which comes from the hidden layer, is aggregated and then goes into our output neuron. We would put that through a we would put that through a sigmoid function. Same if we have multiple classes. If we have C classes, then we would just use the generalization of binary classification. We use the cross entropy loss function, and we use the softmax in order to normalize the probabilities in our output layer, or to normalize the raw outputs in our output layer so that they are translated into proper probabilities. And just to showcase that, we could also set up a neural network in such a way that we simultaneously train it to perform multiple tasks. A regression task and one classification task, say. So we could have two output neurons where one of them is to solve the regression problem and the other output neuron is to solve the classification problem. And then one output neuron would use a linear activation and the other would use or could use a sigmoid activation. I'm not saying that is the best way to address such a problem, but should you have heard about hurdle models, for example? That's something where you could consider a multiple target learning approach, a learning algorithm that simultaneously pursues multiple targets. Neural networks allow that quite easily, and then we could write down some sort of composite loss function in order to train our neural network. But more on the training soon. Finally, I would like to draw your attention, now that you are already quite familiar with neural networks, to a great website which Google created. It's the TensorFlow Playground, which you find at playground.tensorflow.org. And this website provides a graphical user interface to play with neural networks. And it's really nice. I like that site a lot. Maybe I'll spend a little time to navigate to that site. Here we are. That's our playground. And the idea is that we can interact with some neural networks. We can design neural networks and apply them, train them on artificially generated data. So what do you actually see here? Let's start at the top. We have a play button, which will kick off neural network training, something that we still need to look at. Then there are a bunch of neural network parameters or learning parameters. You should recognize regularization and be able to make sense out of the settings L1, L2 and none. But generally we don't need that so much right now. More interesting for us, we can select between two problems. One is classification and the other is regression. That makes sense, right? Let's stick to classification. And then for each type of problem, we have multiple toy data sets that we can select. So here is a checkerboard type of problem. Here we have a classification problem where the two classes or one class is encompassed by the other. Here we have a classification problem where there are just two multivariate Gaussian distributions generating the data points of each class. Checkerboard problem, and last but not least, a difficult one. This problem is called the spiral problem. Guess why? Where you see that the class boundary is extremely complicated. And equally, if we go for regression here, we only have this type of problem. Or no, we can select between two types of problem. Classification generally is a bit more interesting. Let's stick to that. Starting with a very simple example. They're all binary. And because all our classification problems are binary, referring to the table just shown, just quickly, that might help to convince you that the table has a purpose. For binary classification, right? I was stating that we need one neuron in the output layer. Same for regression. For regression, binary classification, we need one neuron only in the output layer. And that is also how this TensorFlow Playground is set up. Here we have our output, and we have that's basically the single neuron we have in the output. And you see how this is then nicely visualized by means of a picture. But essentially we have one output neuron. We have two input features, which is to facilitate the drawing, x1 and x2. And then we have the space spanned by x1 and x2. And the color, on the one hand, it encodes the two classes, yellow and blue. And the shades encode how our neural network basically classifies the whole area all the combinations between x1 and x2 in the interval +6 to -6, where darker blue indicates a higher belief that a data point in that region belongs to class blue, and more yellowish background, which we don't see at the moment, indicates that the network believes a data point in the corresponding area to belong to class yellow. 2 inputs, 1 output, and currently our neural network has 2 hidden layers, the first of which has 4 neurons or hidden units, and the latter one having 2 neurons. It's a very simple problem for now, so let's make our network a bit simpler by killing... Oh, I can't kill that. Okay, well, can I not? I thought I could, but it doesn't seem to be like that. So apparently here with TensorFlow, sorry, silly me, of course I can kill it. Here, now we have a neural network with 1 input, 1 hidden and 1 output layer. That's pretty much what we have seen many times on my slides. And we can now start the training, which will kick off the algorithm that adjusts the connection weights. TensorFlow Playground encodes the magnitude of connection weights with the thickness of a line. You see, if I go over these lines, I get some information. So currently here we have a weight of -0.41, here -0.41, -36, 2.9, etc. And if I click play, we will measure the loss between our class predictions and the true class labels for the training data using the cross-entropy loss function. So if you see some loss here, that's the output of the cross-entropy loss. For classification, for regression would be squared loss, right? And well, the minimization of the loss, that is what training is all about. And we can kick that off here with play. And you will see that very easily loss drops down to almost 0. And we can keep training our neural network, but nothing really changes because the classification problem is very simple. And this architecture, 2 inputs and 4 hidden units, is more than enough to separate the classes. So actually, if we further reduce that, what's that? 2 inputs, 1 hidden, so aggregating the value of input times the weight, adding some nonlinearity and an output. That's actually logistic regression in TensorFlow, right? So if we run that, we would expect, actually we already see that just with the random initialization of the weights prior to training. These values here, these -0.22, they're just randomly generated. Yeah, there we are. That's logistic regression, right? That's our linear classifier, which is more than enough to solve this classification problem because it's so easy. And that is something interesting, I believe, because if we add some more of these computational units, these hidden layer neurons, and some more, you see how the shape of the class boundary changes and now looks something like, our model now looks a bit like a squared classifier. These shapes, they look somewhat squarish, right? If we train our model, the model learns that for this simple problem, it's more than enough to do a linear separation. But if we pick a more complicated problem, like this one, clearly we could not solve this problem with logistic regression, right? I mean, the model has no chance whatsoever. It can only fit a line. That's logistic regression. It can put the line somewhere, and it puts it here because then the loss apparently is minimal. But obviously this is not a very good classifier. But we have just seen that if we add some more hidden units here, we equip our neural network. It's not heuristic regression anymore. Now it's a neural network. We equip it with the ability to perform a nonlinear type of classification. And wow, wasn't that cool? It took a little while, but apparently the network has learned this pattern, that the blue class is encompassed by the yellow class. And it only took us these 3 hidden units to equip the network with sufficient capacity. We could make our problem a little more challenging. If we add some noise, then the boundary between the classes will be a lot harder to estimate. You see how it's getting more and more difficult. Let's see, does the network still succeed? Oh, wow! Very good. So that's really at least a graphical, not proof, but demonstration, how these networks, even if they are simple, can approximate nonlinear functions. Well, if we give the network the most challenging task, maybe this architecture, probably this architecture is not strong enough. You see how it gets trapped. It fits a linear classifier to that data. Although we see immediately that the true class boundary is far from linear. It's a highly nonlinear problem, but this network really can't detect. It is not powerful enough to detect this high degree of nonlinearity. And you see that the loss, right? It doesn't change anymore. Our network training has stalled. Well, I don't know whether I will succeed without using one of the upper parts here to make our network complicated enough to cope with this problem. But we can certainly try a little more complicated neural network. We just add a second hidden layer. And then we have 4 units in the first hidden layer, and then 2 in the second hidden layer. And now we train our neural network. And although we might not yet succeed with this type of problem, at least we see that even after a while, the loss, the training loss, still decreases. And you also see how the weights change, or at least you see how the output changes by looking at the shades in our plot at the right-hand side. More and more areas get classified the longer we train as either blue or yellow. I mean, of course, that is a very challenging type of classification problem. And still our network is not so powerful. I haven't really tuned it. And I think now we arrived at a point where we don't improve anymore. All right. Why don't you spend some time playing with this site? First, you can convince yourself how neural networks are able to approximate highly nonlinear functions, and play a little bit around with these parameters if you wish. Maybe you find a good configuration to solve the spiral problem, and if you did, why not posting that on the Moodle forum so that others can follow up on that and also solve this challenging problem. I think I'll stop that here, rather go back to my slides for summing up. So that is the end of the second chapter. We have learned about the building blocks of neural networks, most importantly the perceptron classifier, which describes a single computational unit, and out of many of these units we form a neural network. And we have seen how by putting some data through a neural network with given weights and given configuration, given architecture, we can generate outputs, we can generate forecasts, class predictions or class probability predictions, or, well, forecasts for regression problem. And we have at least scratched the surface of measuring the loss associated with these forecasts which in the next session will prove the key ingredient for training neural networks as we have already seen it, at least visually, at TensorFlow. So by now you understand neural networks of a set of interconnected computational units that follow one another in a layer-wise structure. And drawing to my table, which I invite you to take by heart, I believe it's important, you have seen how at least some parts of the architecture of our neural network, especially in the output layer, depend on the modeling task that we face. As far as the hidden layer is concerned, we have much freedom, how many layers and how many hidden units per layer. Again, referring to TensorFlow for a demo or the TensorFlow playground. But when it comes to the output layer, we must carefully ensure that what we do there, how we set up our network, that this agrees with our task. For instance, for classification problem, we use the softmax layers and then train the networks using the cross-entropy loss function. That's what I mean by architectural dependence. I would invite you to revisit the coding examples that I was showing in the scope of this session that you find on GitHub. You also have seen some posts or some references to a bunch of very nice blog posts that are fun to read concerning cross-entropy, concerning softmax, for example, and also spend some time on the TensorFlow playground. It's fun, and as a matter of fact, I believe it's quite valuable to get a feeling for neural networks. All right, that was it. Thanks for watching. And in the next chapter, we'll dive into the training of neural network and revisit nonlinear optimization as our vehicle to train neural networks. That was it. So thank you for your attention and see you very soon.